This video will show the last two problems from the notes on section 15.4, titrations and pH curves. I highly recommend you work these problems out on your own first and then watch this video if you get stuck or to check your final answers. So we have HCN, hydrocyanic acid, which is a weak acid, and we're going to titrate that with NaOH, sodium hydroxide, a strong base. So this is a weak acid, strong base titration. We're going to calculate the pH of the solution at 3 different points along the titration. In A, we are going to add 8 milliliters of the sodium hydroxide solution to the hydrocyanic acid. And so let's figure out how many millimoles we have of each. Then let's think about how they neutralize. So 5 millimoles of hydrocyanic acid and 0.8 millimoles of hydroxide. All of the hydroxide will react until nothing is left. And we will have 4.2 millimoles left for our hydrocyanic acid. We can also calculate how many moles of the conjugate base we're going to have, how many millimoles we're going to have, and that would be 0.8 millimoles. Divide these by the total volume, the 8 milliliters of base added to the 50 milliliters of acid, and we'll have the molarity, the concentration. Now, since we have the concentration of an acid and its conjugate base, let's use the Henderson-Hasselbalch equation to find the pH. The pH will equal 8.49. For letter B, we are going to calculate the pH at the halfway point of the titration. That's halfway to the equivalence point. And we learned that the pH is equal to the pKa at that point. The pH here is 9.21. And for letter C, we are going to calculate the pH at the equivalence point of the titration. This is where we have equal amounts of acid and base. In letter A, we calculated that we had 5 millimoles of HCN, so that must mean that we have 5 millimoles of sodium hydroxide. So if all of the hydroxide and all of the acid react, we have nothing left. However, we will have some of the conjugate base, the cyanide ion. We will have 5 millimoles of that. And that 5 millimoles of conjugate base will behave as a base and determine the pH at the equivalence point. Each solution of the acid and the base initially were the same concentration. And so if we had 50 milliliters of the hydrocyanic acid, that means we need 50 milliliters of the base to be at the equivalence point. So that is 100 milliliters total. So my 5 millimoles of cyanide ion will be divided by 100 milliliters to give me my molarity. I get a molarity of 0.0500 molar, which I can then put into my ice chart and come up with what I need to solve for to find my pH. Now I'm going to have hydroxide ion, so I can calculate pOH and then go to pH. I also need a Kb instead of a Ka for this because cyanide ion is the conjugate base. So to find the Kb, I take the Kw divided by the Ka, 1 times 10 to the negative 14th divided by 6.2 times 10 to the negative 10th. That will give me my Kb, and that will be equal to x squared over 0.05. I make the assumption that x is going to be very small because the Kb is small, and so I turn 0.05x into just 0.05. Solving for x, I get 8.98 times 10 to the negative 4th molar. This is my hydroxide ion concentration, which will give me pOH, and then I can convert that to pH. pOH is 3.05, pH 10.95. Throughout parts A, B, and C, the pH has increased from 8.49 to 9.21 to 10.95 as we have added a base to a weak acid. We have talked about how the pH for a weak acid titrated with a strong base at the equivalence point will always be greater than 7, and we see that here. For our second problem, we want to determine the Ka value for an unknown monoprotic weak acid. So the chemist dissolves 2 millimoles in 100 milliliters of water. The chemist then adds 20 milliliters of 0.0500 molar sodium hydroxide, and then the pH is 6. So for our base, 1.00 millimoles has been added. The acid was at 2 millimoles, so we are halfway to the equivalence point. And if you remember, pH equals pKa. We know that the pH is 6. So to solve for Ka, we will do 10 to the negative 6th, or more traditionally, 1 times 10 to the negative 6th will be equal to the Ka. Easy. You might ask, what do I do if we're not at the halfway point? How would I solve this problem? You could see how much of the acid is reacted by the base. This would be the concentration of the conjugate base as well. And then you could use the Henderson-Hasselbalch equation and solve for the Ka value, substituting in the pH and the concentration of the acid in the conjugate base.